Hi, good morning, everybody. So we'll get started. I guess the format will be that we'll do in the order that's in the brochure or in the pamphlet, just so it doesn't confuse anybody. And then we'll start with myself. My name is Paresh Patel. I'm the CEO and founder of Verde Mobility. I also have that's a subsidiary of System Level Solutions, and System Level Solutions actually designs all sorts of embedded systems and things like that. And we started Verde Mobility as a charging company because we used to make traction control systems for locomotives, which is taking dirty AC energy, converting it to DC, and converting it back to AC to run the induction motors. So charging was kind of a no-brainer for us, since that's what we started. But I'm here to tell you about all the other stuff that we've done over the years. We've been a part of the UK smart metering program, where they had to face challenges about grid connectivity and how they get, they have issues when everybody turns on the kettle at 10 and 3 p.m., right? So they get a big surge in power. And so one of the things that we've been thinking about is, how energy and the use of new technologies that are coming in for generation and demand for energy has affected the grid. So anyways, this is kind of a very general overview, because I can talk about this forever and bore you to death. But I'll try to bring out the highlights of this, and then as part of my presentation, I just wanted to make sure that let's see, where's the next one? It shows it on my on this laptop, but I don't see it come up on the screen. Yeah, I'm just doing the next one, so it's here, right?
Yeah, it's supposed to be.
Which one was that?
It's just enter.
Oh, okay, it's just enter. Okay, great. So, at the end of this thing, what does grid responsiveness really mean? I mean, how many of you are in the energy sector? Right, so you probably, a lot of this is just probably a rehash of what you already probably know, but we'll go through it again anyways. And then, yeah, what does, it's not synced here, so sorry about that. What does demand side management really mean? And then we'll go and talk about what's the direction moving forward. So let's get into this. The grid should maintain in European nations and other places either 50 hertz or 60 hertz. And depending on where you're located in the world, it's either 50 or 60, right? So the idea is to maintain that frequency of 50 or 60 hertz, which is the normal range. And if it goes above or below that, you're in trouble. So with some margin. So here in the United States, we have balancing authorities, right? And this was as of 2019. I don't know if Texas has added one more, but the challenge is that you have all these generators, and then you have a supply and a demand for this, and you have the demand. And balancing the grid is no easy task. And you can see in the United States, you have various localities that have a lot of various places, authorities that either buy energy and then quickly make it over, or make decisions on where that energy should go. Because once you generate the energy, it has to flow somewhere, and if there's no demand, what happens? And if there's a high demand, like I think 2 years ago in Texas, where there's that snowstorm, and supplies went from 25 cents per kilowatt to $3 per kilowatt because they're purchasing from other places, and that one authority was there and got hammered too for it. So anyways, that's the scenario that's there. You have a lot of agencies that are handling this and authorities that are handling it, but how do they handle it? What's the scope of this one? And so by the end of this, you'll realize a lot of it is based on software now, and let's get into that. So here's been the traditional grid, right? You've had your generators, your hydro plants, your power plants, your nuclear plants, and then you have your consumers, which are your houses, factories, cities, public other places. So you have the generation side, and you have the consumption side, and all of this you're trying to balance at, in this case, 60 hertz, right? And so now in this new economy, we have some extra generation capability, and there's one more that I need to add to this. So you have, your solar plants, you have your wind, and now we're looking at hydrogen as well to help supplement that. And then in this new complex grid, you have now smart houses and electric vehicles that are additional to that, and there are other power consuming areas. So again, to maintain and do this, you need a smarter grid, right? So to maintain the 60 hertz that is there, you definitely need a smarter grid to make sure that you have your balance of your generation and consumption, and especially with EV chargers. So now you have EV chargers, and they actually, if you're talking about putting 11.5 kilowatt AC chargers everywhere, where's that power going to come from, right? And how are you going to balance the grid when you need that power? And then that's just AC chargers. Like the average in the UK extra power that they have in many places is about 3.3 kilowatts per household. I'm not sure of the number in the United States, but it's got to be maybe just a bit higher. But then when you're looking at, I was driving a Ford F-150, okay, and that had a huge battery in it. And if I charged it for 1 hour on a 3.3 kilowatt supply, it gave me 2 miles. Right? And that put me in trouble. And that's what I can understand people's range anxiety because of that. So now, so then I went to a charger that had 11.5 kilowatts, and it took about 2.5 hours to give me 50 miles. And then finally I went to an Electrify America charger, which gave me 380 kilowatts that are there. But actually, the Ford only charges it for 10 minutes at 175 and slowly starts dropping down to basically when it's at 80%, it'll go down to 30 kilowatts. So that's how the charging cycle works. So when we're looking at electric vehicles, basically, like the F-150, not only can it consume energy, but it can also deliver energy because you have the vehicle to grid and then the grid to vehicle. So the vehicle to grid is where there's a chance to actually balance power. As you're getting extra consumption, maybe the utility can decide to suck up some of that extra energy and put it back into the grid if there's a high demand response. And then managing that kind of spin cycle is because every time there's generators being generated, it spins up and then spins down. There's a lag that's there. And some of the new technologies, which I didn't also show on the kind of the one in the middle line, which is a consumer and a generator, is you have battery systems that you can put to basically kind of absorb small peaks and valleys in the grid and the generation. So that leads us to how do we manage that? And so then there's a demand side management mechanism where major strategies are, the first one is energy efficiency. So that means that let's just design stuff that's energy efficient, right? You went from incandescent bulbs to fluorescent bulbs to LED bulbs. So that did a big difference, and that's one strategy that people used. In India, they're trying to make, the government has mandated that all the wire-wound motors that are there convert to BLDC motors. So you have, 120 watts versus 20 watts times 1 billion plus. So you can see, the delta of 100 watts times a billion can save quite a bit of energy there. So that's kind of the first and foremost thing. Now, once that happens, there's also other things that should be considered. It's time of use. So now this is where you're starting to change people's behavior a bit as well, right? And so when you put a time of use in place, like, from midnight to 5 a.m., your energy price will be lower. So that's probably the best time to charge a car, right? The energy price is lower, you get more bang for your buck, so to speak. And then you can change behavior. In the UK, for example, between 9 a.m. and 3 p.m., it's peak tariff. And then it drops down on the tail ends of that, and then in the evening times it's even lower. But they want to, start having people switch off or switch on the kettles in a staggered manner. And in Finland, we had a project where we did an in-home display to look at, customer use and how they're using their time of use. It was an in-home display that you can set the time of use of what they wanted to do. And what they were actually allowing customers to at that time is to opt in to various events, load shedding events. So if they knew that, based on predictive models, I don't want to say AI, but it's overused, but based on predictive models, they're looking at the trends, and then the next day they know that it's going to be a high event. They'll send a message to the in-home display to the end user and say, are you going to opt in to basically turning off a few things for like 15, staggered away 15 minutes, a particular piece of equipment doesn't turn on for them, an air conditioner and a heat pump or something like that that generates a lot of energy. Then there's a spinning reserve. So spinning reserve, basically the backup generators and other things like that, that's mostly on the tail end where the end user doesn't see it, but the battery energy management systems and things like that that are there. And then we have finally a demand response. So what I told you in Finland was a demand response, where that was a kind of a manual demand response type of event. And then nowadays you're looking at automated demand response. So you have a group called OpenADR, which is Open Automated Demand Response, where you can take APIs and plug them into various big pieces of machinery. And then that basically goes back to the DISCOM or the utility, which then can basically have the ability to push up or push down or basically turn off a load for you. And so those are called ADR type of things. And chargers kind of fit into that last category, where we can actually configure chargers to do demand response on a local level, like when it's not connected to any sort of network, or we can basically make it such that the utility can come in and do some demand response as well, automatically. So the direction is that, so we have all these terms that are floating around. So we have, grid to vehicle, we have BESS, which is battery energy storage systems, V2G, vehicle to grid, we have time of use, we have automatic demand response, and then yes, I hate to use the AI/ML type of thing. I'm old school, by the way, and so those are just some of the systems that we've been using for 20 years, relabeled, right? And so we're just extracting data and looking at trends and trying to predict the future. We've been doing that for ages, and now it's termed AI and ML. But anyways, those are the strategies that people are using to basically come and manage energy and trying to balance that grid where it's at 60 hertz. And a lot of it, and now basically a lot of it is mostly software driven. You have to have the consumer and the generator actually working closely together to make a better impact on some of this stuff. And when utilities here don't necessarily have access into a big plant to basically, shut off loads. You wouldn't want to do that, right? So there's places where that makes sense for utilities to say, hey, we have load events, is there extra machinery that you don't want to put into production, or you can afford not to do it, you can shut those down. That happened in Finland, and there was a mixed response on that one, that some of them were, yes, we could do it because they had equipment that basically they didn't use for quite some time, or they didn't need to use it for that day, and so they opt in. In other places, everybody said, no, never do that for us. So, and I think in the United States, I think the latter would apply. But anyways, the software is there. There's all sorts of APIs that people can integrate as long as the consumer wants that to happen. And where where we can get some gains is in our EV charging infrastructure that's being rolled out all across the United States, where we're going to have battery management systems in place. We're going to have probably hydrogen fuel cells that that basically go onto the and create energy for a charger. We'll have other mechanisms, solar and other things like that, that are charging the cars. And so at that point in time, that's an ideal place where you're not infringing on anybody's rights, but you're allowing people to charge maybe at a lower thing. And I'll give you an example of what I mean. So here we have an unoptimized charging. Here, I apologize, I don't have a pointer. But basically, if you have, let's say, a master charger that has a bunch of piles that are sitting on there, the master charger can have, quote unquote, in this case, doesn't have the brains. So all of these are looking at 30 amps. The master charger is delivering a full 30 amps to this. And maybe I should say 300 amps to make it more impressive. But 30, 300 doesn't really matter. It's that this charger has no capability to actually manage loads or do anything like that. All it does is, there's a car that approached me, let me put in the 30 amps that it requires, or the 300 amps that it requires. So, and so basically that can tax the grid. There's no intelligence there. The idea then is to have a master charger that actually is talking to a server, that's talking to some sort of management system, that also, and the grid is tied into that. That could be utility operator or the charge point operator that has notifications to the grid as well, wherein the master charger still can deliver, let's say, 100 or 1,000 amps, but it basically, first of all, you can add more chargers to this because now you have dynamic management on the charging level. So essentially what happens is that each charger knows cars are in different states of charging. Cars, let's say, near the tail end of the thing, if you have all the bays occupied with cars, and then an extra cars come in, they'll be at different states of charging. The chargers can know this and then appropriately apply the amount of energy that the car needs, and still maintain basically the 100 or 1,000 amps that it can eventually deliver. So you're not exceeding the allocated energy that's been allocated to your system, but and you can get more cars in. So that's where you have the master charger having the capability to understand the, have a little bit of smarts in there to understand what's going on with the cars that are pulling in, and then appropriately deliver the energy. So if I had one car here and I had, my charger was able to deliver, it'll just deliver at full power, right? As more cars come in, it'll start lowering the energy depending on where the car is in the charging cycle. So, and then that all keys back to, let's say if we do have an instance where we would like to exceed that, then you can talk to the energy company and say, well, look, do you have extra supply? Let's pump some more energy through this. So you're always being efficient about what there is. And then when you have a battery management system that's attached to this, or some sort of solar or hydrogen or some generator, you can actually send energy back to the grid when you're not using it, if the grid needs it. So those are kind of the strategies that you can use with chargers that doesn't kind of impact the end user and the utilities are happy, because it's kind of a neutral place where you're not really going off and saying you must do this. The charger manages all of that. So that's where I see that, in this new charging infrastructure that we're putting in place in all of America, these types of strategies need to be put in so that we can manage the grid a bit better. So anyways, that's all I had for today. And if you have any questions, I'd be more than happy to take some. No? So off to our next speaker.